In this lecture, we will start Chapter 2, and what we'll cover here will be functional groups and the nomenclature of organic compounds. We will cover these subtopics here, functional groups, we'll define that. We'll cover saturated hydrocarbon, define that word, and we'll classify alkanes or hydrocarbons, and then we go into the systematic way of naming organic compounds. Let us look at functional groups. First, let's do a definition. A functional group, by definition, or one definition of a functional group, is a region of an organic molecule where a reaction will occur. So that becomes very important when we start looking at reactions. Another definition is a region of the molecule where we have a fixed arrangement of heteroatoms, typically heteroatoms. Remember, organic compounds are, by definition, carbons that contain organic compounds contains mostly carbons and hydrogens, but they do contain heteroatoms like oxygen and nitrogen, and of course halogens. So wherever you see a heteroatom, it will be a functional group. Notice the fixed arrangement in these heteroatoms, oxygen and oxygen. So what we'll do in the next few slides is we will be able to identify these functional groups and we'll give it a name. That's important. We'll need to know the name of these functional groups, because that is how we will communicate. Before we do that, however, let us look at saturated hydrocarbons. In other words, hydrocarbons that contain only sp3 hybridized orbitals. So they're saturated. In other words, they have no functional groups. They're just saturated hydrocarbons. So just to refresh your memory, here is a molecular formula, here's a structural formula, and here's a line angle formula. So you should be familiar with using any one of these formulas, but most important, we'll use the line angle formula very frequently. So you should be able to draw that. In organic chemistry, we typically classify compounds. Of course, as you can imagine, there are literally millions of different types or different organic compounds. So we can study them based on a classification. Here's one way of classifying hydrocarbons. If the carbon is, here's a carbon, if it's attached to one alkyl group, it's called a primary carbon, and we just use a 1 superscript 0. If a carbon is attached to two alkyl groups, remember we're defining alkyl groups here as carbon containing groups, it's defined as a secondary carbon, and we will more than likely just use 2 superscript 0. And of course, as you can imagine, a tertiary carbon has 1, 2, and 3 carbons or alkyl groups bonded to that carbon. So for this portion of the slide, you should be able to look at any alkane and classify each carbon of that alkane as primary, secondary, or tertiary. That's very important when we start looking at reactions, because the reactivity of the groups bonded to that carbon or those carbons are different. So make sure you can identify a primary, a secondary, or a tertiary carbon. Let us look at nomenclature of compounds that contain carbons and hydrogens, but in this case it's not saturated. So we have sp2 and sp3, sp2 and sp carbons. Okay, so the name is, if you have a carbon-carbon double bond, it's called an alkene. And unfortunately or fortunately, you'll have to memorize this or have available a sheet that shows this. If it's a triple bond, it's called an alkyne, A-L-K-Y-N-E. And of course, if you have this system, here's a six-membered ring with 3 double bonds in the ring, it's called benzene. So once again, you should be able to recognize these functional groups in an organic molecule. Here's some more that we need to cover. We have here an aldehyde. An aldehyde is a functional group in which the carbon is bonded to an oxygen by a double bond, and it has a hydrogen bonded to that sp2 carbon. And of course, the other bond is to an alkyl group or a carbon-containing group. A ketone has 2 alkyl groups. Notice no hydrogen. A carboxylic acid has this feature here. Notice the atoms, they must be arranged in that manner to be considered a carboxylic acid. A carbonyl, a carbon bonded to a oxygen, double bond, bonded to an alkyl group over here, and most important, bonded to an oxygen, which is bonded to a hydrogen, and that's a carboxylic acid. Of course, a common carboxylic acid that we're familiar with is acetic acid. Here's an ester. An ester here is a functional group that has the same feature, but here the oxygen is bonded to an R group and not a hydrogen as the carboxylic acid. So notice the difference. There are subtle differences here between these functional groups, and you'll have to recognize these functional groups to name it, number one, and number two, to carry out reactions on these functional groups or molecules that contain these functional groups. Here's an alcohol. We're familiar with that because the fuel is methanol. So here's an alkyl group, and it's an O bonded to an H. So it's an OH that's bonded to a carbon. An ether is an O that's bonded to 2 alkyl groups. So an ether contains an oxygen bonded to 2 alkyl groups. So you should be able to recognize, identify these functional groups in molecules and be able to name them. Here's some more. Thymine is a nitrogen that's bonded to alkyl groups or hydrogen. Notice if we have 3 hydrogens here, that's ammonia. So you need at least 1 alkyl group here for it to be considered an amine. Here's another group, nitrile, carbon, nitrogen, triple bond. And here's another one that's very important, especially in biology, the amide group. It's a carbon-oxygen double bond bonded to a nitrogen, which has 2 alkyl groups or 2 hydrogens bonded to that nitrogen. So notice again that these functional groups look very similar, but there are subtle differences. So you'll have to recognize these differences and be able to identify and name them. As an example, here are 2 compounds that we are very familiar with, and that is, of course, here we have rubbing alcohol. You recognize that as the OH. I hope you recognize that carbon as bonded to 1 and 2 other alkyl groups. So that's a secondary carbon. So later on we'll see that as a secondary alcohol. Here is acetone, a common solvent. And this has here a methyl group and a methyl group here. And here is that functional group here for the ketone. You should be able to identify these and other functional groups in molecules. So let's go back to our original slide and see if we can identify these now. Well, they're shown. So here's the carboxylic acid. Notice it's the entire group. Here's the carboxylic acid. So we cannot say this is a ketone and an alcohol. It is the entire group. Same for the ester. It is the entire group here that is the ester. So we cannot say again it is a ketone and an ether. Another ester over here. And here is an amine, because this nitrogen is bonded to one group and an alkyl group here and another alkyl group here, and that is the amine. Of course, this is the benzene ring. Okay, that's a very reactive, well, it is a ring, it is a molecule that will undergo different reactions that we'll see later on. So, let's see if we can apply what we have just learned. So one, of course, as you know, one of my emphasis for this course is conveying concepts to you, making sure you understand concepts, make sure you understand the different material, but equally important is you should be able to apply that concept to solving problems. The application of that knowledge. So let's look at this and see if you can answer this question. And I'm going to underline the important aspects. So you have to read your questions and understand what's being asked. And of course, then you analyze each of your possible choices. So which of the following classes of compounds is the oxygen bonded to the hydrogen? So we need an OH bond. Is it an aldehyde? You may remember that the aldehyde has a hydrogen, but it's bonded to that carbonyl carbon. Is it a carboxylic acid? Could be, because we have here an R and a carbon oxygen double bond and an OH. So there's the OH. Is it a ketone? Ketone contains a carbon oxygen double bond, but that carbon of the double bond is bonded to two alkyl groups, not a hydrogen. Could it be an ester? Remember, the ester looks very similar to the carboxylic acid, but the hydrogen of the carboxylic acid is replaced by an alkyl group. So you may want to pause your video here and think it through carefully and see which is the best selection. The next slide has the answer. So the next slide here is no surprise, because as you can see, the carboxylic acid is this, and an O and an H. So here is the O that's bonded to the H. So you should be able to apply this to answering questions of this type. Okay, let us go on. What we'll do here is we'll look at the nomenclature of alkanes. So know that we have identified the different functional groups, and we have also identified what is an alkane, a saturated alkane. Let us start our naming system. The naming system that we'll use is the IUPAC, and that stands for the International Union of Pure and Applied Chemists. So what you'll see from here on is basically that acronym, IUPAC. And that's a systematic way of naming organic compounds. So if you name an organic compound and you write that name down, any chemist should be able to understand what that name is and in fact draw or visualize the structure of that name based on that name. So let's look at this. So if you have a straight chain alkane or hydrocarbon or saturated hydrocarbon, it's simple, because you just have to look at these names here and use it. If it's one carbon, it's called a methane. If it's two, ethane. 3-propane, 4-butane, etc. So what you'll have to do is to memorize this or have available a little cheat sheet whenever you take your test or your quiz, so that you will remember the relationship of number of carbons to the actual name. So if it's 6 carbons, the name is hexane and not a 6-carbon compound. It's hexane. So that's easy for this straight chain. Let us look here now at branches. So if there are branches on the alkane straight chain, how do we name that? So let's see. Let's start with this molecule down here. So we identify the longest continuous chain of the alkane. So here we have 1, 2, 3, 4. Or we could go 1, 2, 3, 4, 5, and 6. So the longest chain is not 4, but it is 6. We name the alkane based on the 6 carbons. So the longest chain has 6 carbons. 6 carbons corresponds to hexane. So the root name or the basic starting point of that name would be hexane. We start numbering from the branch, closest to the branch. So you see here we could start here, or we could start our numbering here. But here's the branch. So starting here is closest to the branch, so that's why we start our numbering in that direction. Why do we have to number it? We have to number it because we have to identify the location of the branch. The branch here is in position number 3. So let's see how we put this all together to come up with a name. My suggestion is to start naming at the extreme right. So we start by putting hexane. That's because it has 6 carbons. Next, we indicate the branch. So this branch has 1 carbon. 1 carbon corresponds to methane. Since it's a substituent and not the name of the molecule, we change that methane to methyl. So we have here methylhexane. You can see we're building the name. Next, we'll have to indicate the position of that methyl, because it could be anywhere on that straight chain. We indicate that position with a number. This number right here. So it's a 3-methyl. Notice here we're very specific. A number is separated from a letter by a dash. So make sure you put that dash in. So the name is 3-methylhexane. Let's look at another example here. Let's see if we can name this molecule. So again, it has 1, 2, 3, 4, 5, and 6 carbons. If I were you, I would double check to make sure that we start from the correct end in naming. So we could go 1, 2, 3, 4, 5, 6. But here's the first branch, and it's closer to this end compared to this end over here. So the numbering goes from left to right. Since it's 6 carbons, hexane, here's our hexane. The branches here, it has 2 branches in this case. 2 methyl, 2 of the same. So it could be methyl-methyl, but to save on space, we say a dimethyl. 2 methyls. The di here means 2 methyls. So of course, as you can imagine, if it were 3, it would be trimethyl. Since we have 2 methyls, we have to indicate the location of these 2 methyls. It's on carbon number 3, the first one, and also on carbon number 4. So we put 3,4-dimethylhexane. Again, notice that the numbers are separated by a comma. You will have to put that in. We do subtract points for leaving out the comma or the dash. And of course, as I pointed out earlier, the number is separated from the letter with a dash. So make sure you put those in whenever you're asked to name a molecule. So let's pretend here that you did not see this name down here and you're asked to name this. Start at the end closest to the branch, so more than likely here, because here are the branches. So it will be 1, 2, 3, 4, 5. Since it's 5, it's a pentane. Notice not a hexane anymore because it's 5 carbons. It's a pentane. We have 3 methyls, 1, 2, and 3. So it's a trimethyl in this case. The methyls are on carbon number 2 and carbon number 4. So it's a 2, 2, 4. Notice we separate the numbers by commas. And we must indicate a number for each group. So therefore, since we have 3 groups here, we need 3 numbers over here. So the numbers are separated by commas, and the numbers are separated from the letters with a dash. So this would be the IUPAC name for this molecule. Another example here. So let's look at this one. So give the IUPAC name of this molecule. The longest continuous chain here has 7 carbons. 1, 2, 3, 4, 5, 6, 7. Notice even if we went in this direction, it is still 7. You have to check carefully to make sure that you have the longest continuous chain. So since it's 7, it's a heptane. Heptane. And we have here the groups on this longest chain would be a methyl and a ethyl, because that's 2 carbons. So ethyl for 2. So now we have an ethyl and a methyl. We list them by alphabet. So since E comes before M, this goes first. And of course we indicate where that ethyl is. It's in position number 5. Next comes the methyl, because M comes after E. So we have methyl heptane, and we indicate the position of that methyl with this number here. So you can see it's very important to number your chains so that you can put the groups, you can number the groups in the right position whenever you're placing the name or coming up with a name. Let us look at another example here, and this time we have a halogen. This should not be a surprise based on the name. So again, we start here, that carbon, because that's closest to the branch. Well, the branch is actually here. So we go 6 carbons, hexane. And here we have the groups, the chloro group and the methyl group. But since C comes before M, the chloro comes first, and we'll have to indicate the position of the chloro with that number. And we have to indicate the position of the methyl with this number here. So that would be the complete IUPAC name for that molecule. So let's see if we got this. So the question now is, what is the IUPAC name for the molecule shown here? So you need to start numbering. You need to figure the longest chain, and you need to make sure that the rules that we have just discussed are not violated. So let's see how we'd analyze this. Here's a branch. So I would probably start here and move through as this as my longest chain right here with this number 1, 2, 3, 4, 5, 6. So it's a hexane. And we have a group on the second carbon, a methyl, and we have a bromine on the fourth carbon. So let's see which one matches. 3-bromo. This would indicate that it starts there, which is not correct. 2-methyl-4-bromo. 2-methyl-4-bromo. Seems good. But B and M may have a problem there. 4-bromo, 2-methyl, B and M, and 4 and 2 looks reasonable. And 4-bromo, 2-methyl, butane, that's 4 carbons, so obviously that will not be a good choice. So again, you may want to pause here and make sure that you name this molecule and make a good selection, because the next slide has the answer. And of course, it's not surprising that the answer is this one, based on the rules of nomenclature, the IUPAC rules of naming organic molecules. Let us look here at cyclic compounds, cyclic hydrocarbons. Here is a 3-membered ring. Of course, you can't have a 2-membered ring, so the smallest cyclic compound you will have is a 3-membered ring. And this is easy to remember because if it's 3 carbons, it's really a propane, but we add cyclo before it. So for all of these here, it's just a matter of adding cyclo before the name once you have identified how many carbons are in the ring. So you need to identify how many carbons in the ring. Make sure you add the cyclo, because if you do not add the cyclo, it's implying that it's a straight chain. Let us see if we can apply the name for branched cycloalkane, branch. So if there are branches on the cyclic system, how do we name it? So here's an example. We have to define the root. The root is typically the portion of the name that's to the extreme right. It's a cyclic compound, as you can see here, so it's a cyclo. It's 6 carbons in the ring, so it's a cyclohexane. Now comes the tricky part. How do we name these substituents in terms of numbering? Because since it's a ring, there's no starting point for the ring or the end point like a straight chain. So we'll have to tell the reader what is the starting point. The starting point is at a branch. So here's a branch. So in other words, you could not start over here. You have to start at a branch. Once you have identified that carbon, you need to go in the direction of the other branch in terms of 2. So we go 1, 2, 3, 4, 5, 6, and not in that direction. So that's not correct. We go in this direction because of the branch. So again, once you have identified the location of the substituents based on that numbering system, all we have to do is to put in the numbers to indicate the position of the 2 methyls. It's a dimethyl cyclohexane. Specifically, it's a 1,3 dimethyl cyclohexane. Don't forget the commas, and don't forget your dash. Here's another type of compound that we will encounter in organic chemistry. It's called a bicycloalkane or bicycloalkanes. We won't go into much details here because it's covered in the book, but just to let you know, that you have a compound looking like this. Bicyclo means two rings that are fused together. It's not just one ring, but two rings. So how do we name this? We name this as a bicycloalkane. So here is an example. Here we have a bicycloalkane with 1, 2, 3, 4, 5, 6. Here's the other ring, 7, 8. So it's 8 carbons. 8 carbons would represent octane. Since it's a bicyclo, it's bicyclooctane. And we'll have to indicate the position of the bridge. So this is a 2. 2 are the number of carbons in the bridge. And this is a 2. This is the bridgehead carbon here. So it's a 2, 2, 2, bicyclo 2, 2, 2 octane. Here's another example. This has 7 carbons. Here is the bridgehead. And here's the bridge, 1 carbon. Another bridge has 2 carbons and 2 carbons. So it's a bicyclo 2, 2, 1 heptane. That's about as far as we'll go into this, is that you should be able to recognize bicyclic compounds and recognize how to name them. Next, let's look into alkenes. Of course, as you know, alkenes contain the double bond. Carbon, carbon, double bond. So let's see what's the IUPAC system for naming alkenes. Let's use this as an example. This has 1, 2, 3, 4, 5 carbons. As I pointed out, you could start from this end, numbering, or you could start from this end, numbering, because there are no branches. So in this case, you start at the end closest to the double bond. So this end here is closest to the double bond. So we go 1, 2, 3, 4, 5. So it's a pentane, but what we do is we change the A of the corresponding pentane or alkane to an E to get an alkene. So the name is not pentane with an A, it becomes pentene with an E. Once you put an E there, it indicates that the molecule has a double bond. It's an alkene. As you can imagine, the double bond could be anywhere in that pentene, but it's in position number 2 since we started numbering in that position. So this 2 tells us that it's a alkene and the double bond is on carbon number 2. Let's look at this other example. Apply that principle here. So here again, this has 6 carbons. We know we start numbering from here. So it's an hexene. Notice we changed the A from the hexane to an E because it has a double bond. We know we start numbering from here because this double bond is closest to the end. This double bond is in position number 2, so we'll have to indicate that the position of that double bond, which is 2. Of course, if the double bond were here or someplace else in the molecule, we'd have to use a number here to indicate its position. Here's another example. So here is one. So notice again, to name this molecule, we do not start at this end, even though it has a branch closest to that end. But now the double bond takes priority and we start at this end with number 1. So this is number 1, 2, 3, 4, 5, 6. Hexane. We change the A to an E, so it's an hexene. We'll have to indicate the position of the ene. It's in position 2. Notice again we're separating the number from the letter with a hyphen. Since it has a branch, we'll have to indicate the position of the branch, and here it is. So with this systematic way of naming alkenes, you should be able to name any alkene. Here's another example. Again, we do not start here, even though we have a branch here. We start at this end because here is our double bond. So again, 2 represents that ene, and 5,5, notice we have to put 2 numbers because it's a dimethyl. So if you have di, we expect 2 numbers prior to that di to indicate 2 substituents. Also, before I leave this slide though, you should be able to, if given the name of a molecule, you should be able to come up with the structure. So again, working backwards. So practice that. Given the name, can you determine what the structure is? So come up with a systematic way of doing that. My suggestion is to start right here and work your way backwards to your substituents. Let's look here at cycloalkenes or cyclic alkenes. Same trend. If you have a cyclic alkene, you recognize it's an alkene because of the double bond. Determine how many carbons are there. If it's 6, like in this example, change the A from the alkane, cycloalkane, to an E, so it's a cyclohexene. Notice we do not have to put a 1 here because it's understood to be in that position. Same here, cyclohexene. I'm indicating my numbering here because it becomes very important if we have groups or substituents bonded to the ring, which is shown on the next slide. So if you have substituents bonded to the ring, naming becomes a little tricky. Because we have, let's start with this. We have here 6 carbons in the ring, so it's a cyclohexene. Here's the ene. We have to indicate that position. It's a position number 1. Notice we're not starting the numbering at the branch anymore because the double bond takes priority over branching. So you start here. One may ask, couldn't we start over here? Yes, you could. But here's the trick. Once you start, you go in the direction of the double bond. So we go 1, 2, 3, 4. And not the other way. Not 1, 2, 3, 4. We go in the direction of the double bond. So once you have that numbering system down, it's just a matter of putting this as 1 carbon, methyl, and it's in position number 4. And you of course separate the 4 from the letter with a dash. Notice you need not put this 1 in, but if you do, it's not incorrect. As a matter of fact, you may want to do it just to be on the safe side, but it's understood to be number 1. Same here. Here's a double bond. It's a 5-membered ring, cyclopentene. Here's the E, here's the 1, and we number in the direction of the double bond towards our branch. In the direction of the double bond towards the branch. On carbon 3, there are 2 methyl groups, so it's a dimethyl, and it's on the same carbon, so we use 3, 3. Notice you have to use 2 numbers to indicate 2 groups, even though they're on the same carbon. So here's a practical application of this. So let's see if we can answer this question. Which is the line angle structure of the molecule, of this molecule which has this IUPAC name? So it's a cyclohexane. So this one would be questionable. It has here a two groups. Well, let's see. There's a hexene. So the assumption is, since there's no number here, it's assumed to be in position number 1. It's assumed to be in position number 1. And once you have identified that as position number 1, and you go through, so let's see if we can draw that. So we have a position here. So 1, 2, 3, 4, 5, and 6. Notice I'm going in the direction of the double bond. It states on carbon 3 we have an ethyl group, and on carbon 5 we have a methyl group. So let's see which one would match that. So once again, you may want to pause the video here and work this through. Work it through and see what answer you come up with. And let's check the next slide. B. So we have here 1, 2, 3. This would be for my ethyl. 4 and 5. This would be for my methyl, and the 1 for the alkene or the cyclohexene is understood. So notice this would not match. This would not match the numbering system here. This, of course, would not match because it is not cyclic. So be careful with that. So you have to be very careful here. What we'll do here is we'll conclude this lecture at cycloalkanes, and next lecture we'll start with benzene, which I'll post in another couple of days or so. And so in the meantime, read through your chapter in this, follow along with this video here, and of course you'll have a quiz on Thursday, pardon me. And so the material on chapter 2 will be on that quiz. So continue to study hard and be very and consistent with your studying. Okay? Bye.